Thanks. So I will say that this is really work that is a collective effort in the CARRA team. So it's really thanks to many colleagues what I present here today. I just start with giving some context for why an Arctic reanalysis in C3S, why interest for the Arctic. So I think this is something which many people are noticing now with what we call the Arctic implication. And actually this figure I show to the right here is from a set of climate models, the 33 climate models that were basis for the previous IPCC report from the CMIP-6 project. So it shows the warming or the temperature change in the Arctic near surface from pre-industrial time until the end of this century. And this is for an emission scenario which gives global average warming of about 2.7 degrees centigrade. So you see that the geographical distribution is so that this amplifies in the Arctic, and with this global average warming of 2.7, the models give around 10 degrees at maximum in the maximum zone in the Arctic. Slightly less in northern Scandinavia, and Western Europe is closer to the global average warming. So we really see in the models an Arctic amplification. And then, of course, it's also interesting to see if that is reflected in observations and in reanalysis. So that explains part of the interest for an Arctic reanalysis. And another item here is, of course, it's not only the big picture of this average warming, but this is highly varying with season. It warms more in the winter. It varies from year to year and interdecadal due to natural variations also. So the big picture is that the Arctic is really changing now. So a little bit of background now. So in Europe, we don't really have any legacy for Arctic regional reanalysis. We do have a legacy for European regional reanalysis through previous research projects and work in many MET institutes. We have the Euro4M and UERA research project, which has led to this CARRA European regional reanalysis, which is also part of the Copernicus Climate Change Service. But we have no such legacy in the Arctic. So we started more or less from scratch around 5 years ago, and to the right you see the logos for the institutes involved in the CARRA developments. So it's the Met services of the Nordic countries, it's Meteo France, and it's the Danish Geological Survey, the GEOS. So, and this was very much building on experience from operational weather prediction in the Arctic, these developments that we had. Yeah, so now we are in the second phase of Copernicus actually, and in the first phase there was produced a European reanalysis, as Andras already mentioned, the CARRA system, which is the big domain you see here, which is at 5.5 kilometer resolution. It's led by the Swedish Met Service. And then we also have now on top these two domains, the CARRA West and the CARRA East domains, which now are the Arctic regional reanalysis, which we are talking about today. So it's a 2.5 kilometer resolution, and we have a data set running from late 1990 until present, which is led by Met Norway. And now we are in this Copernicus phase 2. So the main activities in this phase 2 is to do timely updating of these data sets. So for CARRA, this timely updating is now ongoing. We do a monthly update, and CARRA, the European reanalysis, they are also working now on implementing a timely updating service to that. So then a little bit about the actual system that we are running for the CARRA reanalysis. You see the domains again here. As I said, we both Norway and Denmark run Arctic operational weather forecasting systems, and the CARRA system takes quite a lot of components from these weather forecasting systems. So we use the so-called Harmony Arom NWP system, which is developed by a European consortium. And on top of that, we have done many extensions for reanalysis to use historical data, etc., and also for applying the model in the Arctic with the special features we have there with having snow and ice, etc. It's a non-hydrostatic convection permitting model with this high resolution, and we do 3-hourly data simulation. We do long forecast from that twice a day. And as Andras also said in his introduction, we have the data are open and freely available in the climate data store. Then a little bit about the data assimilation, how this is done. Andras mentioned we are employing a so-called three-dimensional variational assimilation. So this is kind of standard method that many use in data assimilation. So you have this cost function that is minimized, this J of X, which have 2 terms. The first term makes sure you don't go too far from your forecast from the previous reanalysis, the XB, which in a way carries with it all the previous observation and the knowledge about the physics of the system from the model. And then the second term makes sure you get close to the observations, which is here called Y, and this H is what we call an observation operator, which takes your model to the observation locations and make it comparable to the observation values. So from this, using this error covariance matrix, you get a weighting between these 2 terms, and you end up with the actual reanalysis, which is these maps without gaps that Andras mentioned. Yeah, in our implementation, this B matrix can vary with the day of the year, because the atmospheric flow and its statistics look different in the summer and winter. And then this B matrix is generated from a proxy data set that comes from downscale ensemble from the global reanalysis system. So this is for what we call the upper air assimilation, and we also do a surface assimilation with the SURFX system, so-called, and it's an optimal interpolation system. On top of that, we do some uncertainty estimation, and as Andras said, that is so-called static or climatological uncertainties for the variables, for a selected subset of the main variables in the reanalysis, and that's based on this proxy data set that we use for estimating this B matrix. And we also do some scaling of this towards the actual observation departures that we only find at observation locations, but we have kind of more generally valid uncertainty estimates that you can find on our Confluence pages or download. Important thing to say here is that ERA 5 is a really important contributor to the regional reanalysis. It plays an important role, first because ERA 5 is used on the side boundaries as boundary condition for our CARRA reanalysis, but there are also some strengths in ERA 5 that we want to exploit. That, for instance, ERA 5 use more satellite information, has a more advanced data assimilation method with its ensemble usage and the 4D system. And these boundary schemes are not perfect solutions. So we also use forcing from ERA 5 inside the domain, not only on the lateral boundaries. So this is a so-called large-scale mixing scheme, which is done in a wave number space where we have done a spectrum transform on the field. So this works in such a way that we replace the first guess field in the simulation with the weighted average of the ERA 5 and the CARRA, but that is only for the long waves in the system. So we take the large scale information from ERA 5, and we also have a weighting so that we take more information from ERA 5 in the height than in the low levels. So ERA 5 is really important for forcing our system. So in a way, we act like a magnifying glass. Then I would like to give some overview of the key development elements. I already told that we it's important to build on the experience from running the weather model every day, which forces us to do a lot of quality control on the system we have and make sure it gives good results. But we do several adaptations for use in the Arctic based on our operational experience, and also we spend effort on the surface forcing fields. We put in information about the surface state, and running a 2.5 kilometer system, we have spent much effort to have good spatial resolution and quality in the surface fields we use to force the CARRA reanalysis. I'll get back to that in a moment. And the particular focus is on what we can call cold surfaces like sea ice, glaciers, snow cover. Yeah, and we also do extra effort to get more observation that what is transmitted in real time. Many of the countries have measurement campaigns or climate observing stations which do not transmit data in real time. So we collect data also from archives to use in the simulation in our system. So for instance, we collect data from the Nordic Meteorological Institutes and for Greenland extra observing networks. And for the Arctic, we need to exploit satellite observing system, and we of course for reanalysis we needed to do extra work to exploit the historical satellite data. So some examples of the adaptations we are doing for the actual model. So we're using a special scheme for the snow on the sea ice, which has not been used that much earlier as standard. We have been working with satellite information to take into account the surface contribution to the satellite data when exploiting the microwave sounding data, the so-called dynamic emissivity method. And now I have a slide with kind of a list of the high resolution surface forcing field that we have spent effort on compiling. So we do special adaptations to get high resolution ocean and sea ice fields. We have produced or adapted special high resolution satellite snow data maps to use as surface forcing for CARRA. We do physiography corrections because the standard physiographical databases in the Arctic often have very poor quality, and it's important to describe the ground well. Especially, for instance, like coastal stations where you need to have the coastline right, and we have done a lot of effort to correct using satellite imagery and other data sets for that. We use external glacier albedo based on actual observations from satellites. Yeah, so these are actually examples of the kind of adaptations we have been doing to improve the quality and improve the near surface fields for CARRA. And of course, we exploit the full observing system with both satellite and conventional observations for the upper air assimilation. And of course, with the remote areas in the Arctic, satellites have very high importance. So this shows the satellite observations that we are using in CARRA. So this is a list of present and historical satellites that we are using. So the list is somewhat shorter than the list they use at ECMWF. They use more data than we do, but we think at least we use the most important and the systems that will provide most impact in the reanalysis. And here we also benefit quite a lot from the good work they do in the ERA 5 team and at ECMWF on exploiting these data sets, making available climate consistent time series from these. And we also benefit a lot from the blacklisting they do at ECMWF for when we can exploit these data sets and which channels, etc. Yeah, so Xiao Young will give a presentation later on, and he will probably give some more details about the work in building the actual CARRA system. So then the question is, how does that impact the quality of what we are doing? So this illustration shows a strong wind event over the Spitsbergen area at a given time. It shows the 10-meter wind with CARRA and flipping with ERA 5. So you see that we actually get quite a lot more details. But even if you have more details and more spatial resolution, it's not necessarily so that these small-scale phenomena are predictable. So you could kind of get the climatology and intensity right, but you could get them at the wrong time and place. So we hope that still we improve in that respect. What we are more certain about is that we have quite a lot of forced structures which are forced by topography in the Arctic weather and the Arctic atmospheric features. So we are quite sure that when we improve on this forcing, we can also represent forced structures better. But we have done quite a lot of validation and verification work, and there will be later presentations from Morten Kulso and Jason Box on this. So we look at overall verification statistics versus observations, and it seems that we can add value upon ERA 5 and global reanalysis in that respects. We've also been looking into how do we capture extremes better, strong winds, things like that. For instance, like polar lows that we have in the Arctic, and it also seems we improve on that. Local climate statistics, how do the distributions of the various quantities look in terms of histograms or statistical distribution. It seems also that locally we capture better the shape of the statistical distributions. Climate trends we also have looked into. I set a small question mark on that, but I think in many cases we also see that there are some differences in the trends between CARRA and ERA 5. We might come back to that, and in some cases we think we also represent better some trends that we see. The next one shows the historical timeline for the CARRA 1, the data set, which is available now. So we started in 2017. We started producing in July 2019, and after around 1.5 years, the first data was partly released, the data set. In October 2021, we had completed the full more than 30-year period, and in March this year, we started this monthly timely updating. So the timely updating is done monthly, as I said, and we have the updated data set available within 2 months after the end of the months we produce. There are plans for extensions of the output that we provide now. So there are plans for monthly means and maximum and minimum values to be available on the climate data store. There are also thoughts about easier geographical subsetting of the output variables, which is now being planned. We don't know exactly when this will come. We hope it will come soon. And the present contract for the timely updating that runs up until September 2025. So we don't know whether we will run after that, and eventually we will have this new system that we are working on building now, the CARRA 2 system, and that will take over for the CARRA 1 system eventually. So the main work we are doing now, in addition to the timely updating, is to develop the CARRA 2 system. So we are in a quite intensive development period for this CARRA 2 now. So this will be the next generation Arctic reanalysis, and it will be a pan-Arctic one, as you see on this figure. It will be a much larger domain, and we hope and think that we will also be able to run that at 2.5 kilometer horizontal resolution, which means it will be much more expensive to run, but we are still looking at the configuration, how it will end up. But we hope to have a very good spatial resolution also for the big pan-Arctic domain in the next generation. We commit to producing data at least starting in 1991. It might be that we will be able to also go earlier. And for the new system, we will do quite significant updates in the surface physics to have a more advanced surface scheme and also more advanced surface assimilation. We will also update our uncertainty estimate with machine learning methods. We have a contract now which runs up to 2026, and the plan is to start a production of this system that we are developing next spring. So the schedule for the next generation, the CARRA 2, is we started about 1 year ago with the project. We plan to start the production March next year. Then 1 year after that, March 2025, we plan to do the first release of the partial historical time series. And then March 2026, 1 year after that again, we plan to have the complete data set from hopefully before 1990 and up to present time produced. And after the end of the production, we also will have significant evaluation activities. During CARRA 2, we have continuous user support activities, also to support the use of the CARRA 1 data set. And actually this workshop is part of this activity. And we also plan another user workshop when we have released the complete CARRA 2 data in April 2026. And of course, you as users are very important for us, and we very much welcome your input and questions in the chat in this workshop. So thanks for that. That's my presentation. Thank you.